All right, it's glad to be here. My name is Spencer Patty. I am a software engineer with the Intel oneAPI Math Kernel Library. It's a mouthful. We call ourselves oneMKL now. Used to be just Intel MKL. Let's go into presentation mode, I think. Very good. All right. Yeah, so I'm glad to be here, and we'll do just a brief overview a little bit about what is MKL. I assume many of you are familiar with this already, but maybe there are those that are not. So we are a math libraries group with Intel. Our job is mainly to provide highly optimized math kernels. We've got a lot of domains: linear algebra, FFTs, vector math, RNGs. My particular area is sparse linear algebra. I've worked mostly these days on Sparse BLAS, but I have worked on the different sparse solvers and other different aspects of the sparse world over the last few years that I've been there. We support lots of different languages. Traditionally we've had C and Fortran bindings for all of our functionality. That was for CPU. In the last few years, we've expanded into GPU land, and we're starting to go down this route. We've heard a little talk about SYCL. Intel got behind the SYCL standard and has really been pushing that as the language of heterogeneous compute. There's lots of other options out there. It's a good one. There's lots of other good ones too. But what that means is that in our implementations, we have now SYCL C++ API. SYCL is built on top of C++, currently C++ 17. And so there's a lot of nice features that are starting to be able to be used for these math libraries. And a little bit more detail about all the different areas. In linear algebra, we do have the standard BLAS and LAPACK libraries. Those have been, well, the BLAS side has been completely implemented for CPU, GPU, optimized for Intel hardware. On the sparse side and LAPACK side, we've been more picky about what we choose to implement yet, and we're expanding it consistently every release. We're adding more things. On FFTs, we've got lots of stuff as well. You can see all of these things. We had a graph library for a while. We were going that direction. It's actually going to be removed in the next, it's been deprecated for about a year now, and it's going to be removed in our next release. If you're interested in graph BLAS stuff, go see Tim Davis's nice graph BLAS implementation. He's got some really cool stuff, both for Intel, for NVIDIA. He's been doing some amazing work with implementing the graph BLAS spec. A lot of cool stuff there. And so, like I said, in about 2020, Intel sort of changed our direction a little bit. We added in this idea of, let's think about CPUs and accelerators. And what we created, we added this one moniker onto everything. So there was this umbrella thing called the oneAPI toolkit that was created. And so lots of teams like MKL, TBB, MPI, compiler team, lots of other ones. We all added one onto our name. So officially we're now Intel oneAPI Math Kernel Library. And it has been for several releases. We've got different naming schemes now for things. But we've had a number of basically releases as we've been going down this route, and it's continually building things. We're coming up to our 2024.0 release, which will be end of this year. And lots of cool stuff. And we support a lot of things, CPUs. I'll go into the sort of the latest two CPU and GPU things. A lot of Intel GPUs. There is not currently support for FPGAs in our group, but at some point that may also become something that we're supporting math operations on FPGAs. It's currently lower priority than the GPU work that we're doing, which is what we've been doing a lot of. So the big CPU package, we call it Sapphire Rapids, but its official name is this Intel Xeon Scalable Processor with a big number, all sorts of things. There's a whole lot of cool stuff going on here that has basically added in the high bandwidth memory where we are going away from the single sort of Each socket is a whole bunch of cores. Now each socket has a bunch of sort of chiplets, as it were, that each have their own sort of locality. This seems to be the way of the future. I think AMD picked up on this a couple of years before we did, but a lot of things, each of these chiplet type pieces have their own HBM stack, and so you get all the nice fun, you get the ability for the NUMA nodes and that kind of stuff. Very, very easily flows out of this. Really cool machines. The Sapphire Rapids CPUs with HBM, the big boost is for us in our world, we have a whole lot of memory bound and latency bound. So that addition of HBM really can make quite a difference. And one of the interesting things is that it often changes where the bottlenecks are in our algorithms, because you have so much more high-band sort of this memory flow. All of a sudden you've got things that previously weren't slowing you down. They weren't the bottleneck. Now they are, and it introduces new things. I'm happy to answer questions about this stuff. We can come back. That's the CPU. Any questions about kind of, this is the latest cool CPU thing? All right, yeah.
So with this idea of chiplets as opposed to chips, what is the memory model going to change in terms of memory consistency, or are we still thinking the same memory consistency model as before?
So by memory consistency, you're talking about strong memory ordering. I don't foresee a change to that, but there may be something that pops up that allows for different things. I'm not aware of it, though. It's a great question, because things are more local, and so you can have maybe locally you've got more strong, other places are weak. Yeah, there's a lot of options that can come into play, but I'm not aware of any decided changes in that direction. Yeah. All right. On the GPU side, the big flagship that we've been building up to, this is part of the Aurora stuff, is this data center GPU Max. We call it PVC Ponte Vecchio. It's a beast of a card, and when you have lots of them on there, it's massive. It's fun to play with, and a lot of our work is trying to figure out how do we exploit this. In the sparse world, there's a whole lot of stuff that you try to do, and you end up running into things, especially stuff like triangular solve or sparse triangular solve. There's way more compute units here available than often you have work to be done, and so there's a lot of things like MV, matrix SPMV stuff is very easily parallelizable, but other algorithms are much less so. So trying to figure out how to do these things and how to do them well is a lot of the work that we're trying to do, and fascinating, interesting problems, but you get lots of cool stuff there. Any questions about that at all? All right. So I thought I would touch a little bit on, I went through and looked at how is oneMKL used, mainly used in PETSc. And it boils down to essentially, besides the BLAS and a few small LAPACK functions, really the workhorse pieces are sparse matrix vector and sparse times sparse multiplication. And there's a variant of that, which is we call it the SIPR, function symmetric product. It's essentially a transpose BA symmetric product type operation. You can think of it as composition of two matrix multiplications. And this is the area where we've been looking and working a lot, trying to get SPMV type things, and the name here is SP2M, but it's SPGEM. There's a lot of names out there. Sparse times sparse matrix multiplication. And in fact, probably the last year and a half of my life, I've been really trying to figure out how to do sparse times sparse on GPUs. And there's a lot of room for research, implementing things, trying to figure this out. A lot of fun stuff. As I said, in MKL, we have SYCL APIs, which are very flexible in how you can do things. And we design these things basically having learned from our experiences on C and Fortran, a lot of things that maybe we didn't necessarily get right the first time or the second time or the third time in our math libraries. You'll notice an SP2M there. There's an older API that's SBMM, which was the old one, and before that there was the Sparse BLAS NIST APIs. There's a whole lot of trying to figure out what do we do with sparse APIs. What's the right API? And we can go into that if you guys are interested. There's a lot of fruit for talk. But the SYCL APIs, we tried again to get a little bit better this time. Maybe we didn't get it right. We'd love feedback from people that are using these things. But with the C++ APIs, they're a very C style of C++. Essentially, it's overloading is the main thing that we used from C++. But there's also the OpenMP offload. Some people call it OpenMP target as well. We've introduced a lot of those APIs, which are off of the previous existing APIs that you've probably used for a lot, in C and Fortran types of things. And it's very convenient, although one of the things we've discovered is that there are, for some of these things, especially SP2M, getting performance through OpenMP offload is very tricky. There's some bottlenecks. I'm in work, anyway, I'll be reaching out to some of the developers here with some proposals of a new API that I want to introduce that might alleviate some of those issues on our side with the OpenMP offload at least. So I figured I brought a whole lot of slides and decided I'd love to hear actually from you guys. We sort of plug in on the backside, and it's not very often we get to hear what can we do better, what can we do differently to make you guys' lives better. And I thought maybe if we have some time, just have an open discussion about what is it that you'd like to hear about MKL, what would you like to see? What would be most useful to you from a kernel library like us? I do have a bunch of slides prepared on some examples in C++, SYCL, language, offload as well, some things on the inspector executor Sparse BLAS APIs, as well as our SYCL APIs that are there for that. We could talk about other things, but basically, what would you like to hear about? Yeah. Aha.
Ideally, where the different matrices, they have different non-zero structure and be able to
Okay, so so what he asked for is are we doing batching for sparse? And in particular, there's a lot of ways with sparse things with batching. You could have the same matrix and lots of right-hand sides. You could have maybe the same matrix structure, different data values, so you can reuse the underlying pieces and just swap out the values and do different products. Or you can do the full-fledged batch. I've got a whole bunch of different matrices. What are you going to do? So we have been discussing whether this would be valuable to do or not. On the dense side, we have a whole lot of APIs that implement batching in LAPACK and in BLAS that we've been adding for the last few years. And we have not done anything yet in sparse, mainly because there was this question of what do people need, and not a lot of requests for that. How big of sizes are you talking? Well,
ideally, I guess, a wide range.
Okay.
A particular case where this comes up, one of our very long time PETSc users, going back before even PETSc existed, worked a lot on iterative methods that use decomposition. So inside of them are lots of small, more or less kind of incomplete factorization solves with relatively small matrices. You can optimize these quite well for GPUs. For CPUs, just by writing the correct code and doing them one at a time. But on a GPU, they're absolutely terrible because you can't give a single one of these sparse matrices to the GPU, and then the next one, you're going to get terrible performance. You have to have the GPU doing many of them at the same time. But writing all that stuff as an outsider in the world, as opposed to in the company, is an enormous
ask. Yes. Okay, that's good to know. Are you talking like thousands of these, or tens of thousands, or are we talking hundreds, tens?
Probably hundreds of the
Of the smaller systems, okay. Yeah. So even millions of them with the batch preconditioners.
In that case,
They're very small.
Well, okay, so it can range from very small for like just the HDIV type of things.
Mm-hmm.
You know, hundreds of unknowns for some of the other dispensations where you need a bigger, like for palisades for trying to define it, they can be hundreds of unknowns.
Okay. All right. Maybe I can sit down with you guys afterward and write down all the specific kind of the example problems. That'd be great to get that written down and have an example why that's useful. That helps me make an argument for prioritizing work like that. Yeah. Okay, so the SIPR API here?
Yeah.
And what was the question? What?
Do you do inspector executive for that?
Yes, we don't have the analysis. There's no inspector API at the moment for that. But if there are, we've been able to, the algorithms we've been able to implement haven't required a pre-processing yet. But if there are cases where we could see advantages to doing some sort of analysis of the structures.
Carl has a paper where he goes over various choices and over different ways of breaking it up.
Mhm.
Different algorithms were better depending on the sparsity.
Absolutely, yeah. So this one was driven by a collaboration with another company that they had particular size, and so we added this API in. And PETSc saw that we had it, and I think they started using it as well. If there are cases that we can improve performance for, let us know.
Well, I put in the use of SIPR, right? But we actually only really use that in like the sequential case, right? Because if we have, an MPI parallel, matrix that's symmetric, right? The way you split it up, you end up with non-symmetric things to deal with. So usually we're using the SP2.
Yeah.
I was going to say the analysis part might be useful when you have nonlinear problems that are using either domain decomposition or multi-grid preconditioners, which will tend to have these A transpose BA.
Mm-hmm.
And if, again, you do some nonlinear processes, then you likely will have the same sparsity pattern across nonlinear iterations.
Mm-hmm.
On the problem.
Right.
And the inspector can be, amortized across the whole
Mm-hmm.
nonlinear versions.
Okay, so one of the things that we did implement, and this is what the SP2M and SIPR has, is this multi-stage idea of being able to say, hey, these are going to eventually have the same sparsity pattern. And so you can break it up into pieces. I was actually having a conversation about how we used that earlier. It turns out that the way that PETSc uses it is different than most of the rest of the world that uses it, including our API. So in PETSc, you guys call, it's finalize molt noval, and then finalize, or sorry, full molt noval, and then finalize molt. And so right now, the way we are implemented, we're actually doing redundant work on that second call. We're not taking advantage of the fact that column indices is already created. And so this is a place where we can do better, trying to come up with an algorithm that says, hey, we already know column indices and row pointer if we're CSR array kind of things. We already know sort of the locations of all the non-zeros. Let's just fill in what are all the values, grab all those pieces. That's a place where I think we can do a better job of implementing an underlying algorithm that fits your use case better. Yeah.
I was going to comment that having reviewed some papers that people submit where they're describing new SP2M algorithms, you'll see a lot of papers that are just, we took all of these matrices from matrix market, and we either squared them or we did A transpose A.
Yeah.
Whereas, the performance average over that says very little about things like GA and G. And So seeing things where just take a big 3D CAD model, come up with a maximal independent set aggregation prolongator, use those for the kind of performance measurements. Trying to predict the performance for us is kind of
a better app. Yeah. So maybe we could collaborate and come up with a test for us to add to our performance suites that fits you guys' use model better. More in the sense of it's a prolongation reduction type operation. Yeah, fantastic. That would be, we'd love that kind of a collaboration. Absolutely. Make these things better for everybody. Yeah, SP2M is tricky. One of the hard parts about this API is that we came from a world where we're trying to give performance, but we sort of said we're going to do everything behind the scenes, and so the allocation of the C matrix is internal to it, and we had to add APIs to allow people to get access to those things and copy. What I'm working on right now is coming up with an alternative API which breaks into the pieces, and users will supply the matrix data themselves that we will then fill. These types of changes. We did that directly in the SYCL APIs, but in these inspector executor ones, we haven't had that yet. But I think that'll be something that I'm hopeful that we'll be able to spend some time in the next year to put that in and get that kind of added to our collection of things that we can provide. Just to give a flavor for offload, here are what the offload APIs, the current ones that we have, what it looks like to call them. You got a whole bunch of this ugly pragma business, but it's basically saying, what am I doing? Where are we going? There's 5.0 and 5.1, change some things of how OMP 5.1 and 5.0, we support both of them. They give you different options as to underneath what's happening. The prefer type allows you to specify underneath how it's going to be handled. A lot of nice stuff, but personally I prefer the SYCL for GPU stuff. You can reason a little bit better about all the asynchronousness. Here, all you have is a no wait, and it's basically on the previous thing, so it's almost a linear thing. It's very handy for existing code just to get GPU offload. But really being able to reason through the CPU, GPU nature, having the language abilities like SYCL offers, to me, or a lot of the other languages that do it, give a much richer ability to create graphs and DAGs of dependent events all enqueued on different things. So that's essentially our inspector executor style, analysis executor style, very similar in design. We have a small limited set of APIs that we've been trying to get really right. We're about to start looking into BSR style matrices, but it's almost all our work has been, for the last bit, has been in CSR matrices internally. Eventually we'll expand to lots of other things, but trying to get these right as we're learning how to program on GPUs and get the most out of this hardware. Yeah. Any other questions? Things you'd like to see? Mm-hmm.
Yeah, I'm curious. So one of your slides, you said like when it comes to the GPU offloading, you said you could either use the SYCL C++ or the C Fortran OpenMP offloading.
Mm-hmm.
Can you mix and match like in the same code?
The short answer is I have no idea. I've never tried it. But I imagine, could you do that? You could probably have different objects. So the problem is that the OMP target manages underneath, it manages its own queues of things, and getting access to that to then plug into other graphs. If you've got separate streams, as it were, I bet you could do it. But if you're trying to use the same thing, I don't know that it's possible yet. It's a good question.
Okay, because that is a similar problem we're facing at AMD as well. So just
Yeah, it's a.
It's like if you're never actually going to do it or successfully do it, please try to make the compiler flag same. Understand each other across OpenMP, offload, and actual make it compilation. Because already just compiling for one is hard.
Yes.
So for both is going to be really
Yeah.
compiler flags are going to be tricky.
Was there another question?
I'd just like to comment. This is actually really important from the perspective of a library like PETSc, right?
Yes.
Because we support a lot of Fortran users who, like, if they need to take their physics routine written in Fortran, they are not going to, make that a simple routine somehow. They're going to use something like OpenMP offload. But maybe on the back end inside PETSc, we want to be dispatching, things using SQL. And so, we need a way to let that physics code, get some of the internals of, the vectors and matrices and so forth. And right now, I don't know how to do this in a way that works for a bunch of Fortran applications. So that's something.
Yeah, it's a good point. Maybe it's a good idea to bring a toy problem and let's play with it and see what can be done. Because it's putting them all together is going to be tricky. In fact, offload already underneath the pack, these wrappers. Let me just show, where was it? There it is. So underneath all of this stuff, we're actually calling our SQL APIs. So by linking with OpenMP, we have wrappers that are built into the back end that themselves are calling our SQL APIs. So instead of implementing the same code twice, one in OpenMP offload, one in SQL, we worked with the driver teams to sort of build SQL, which brought a bunch of other things like C++ into the C and Fortran sort of runtime collisions. It's a mess, but I think so far it's working, but we'll see as we continue to grow how things go.
Well, Spencer told me ahead of time that he was going to try and engage us with a little bit more Q&A in his talk, and I think that turned out pretty well. We had a really productive discussion. Thank you, Spencer. Let's thank him one more time.